Hello everybody and welcome back. In this video solution, let's dive into the problem, construct a BST from pre-order traversal. It was quite recently asked on Amazon. The first thing I want to clear up is what does BST mean? BST stands for binary search tree. There are two important properties that we want to keep in mind. First is that y is less than x, which is less than z. This always holds true for a structure like this, where x is the root, y is the left child, and z is the right child. The second thing is this applies recursively. This will become important much later on. The second thing we want to get clear on is what does pre-order traversal mean? Now, if you don't know about it, well, you can just compare pre-order with in-order and post-order traversals. So basically, x comes at the first in pre, x in the middle in, x at the end in post. As simple as that. Again, this is x to y to z, and this is the kind of property that we want to follow. This is also applied recursively. Okay, let's start to talk about observations because this is what is going to get us to the final answer. We'll pull out some very important, interesting points from this. So let's get started. The first thing I've done is I've drawn this sample tree over here, and I've written down the pre-order traversal for this tree manually. So I've done 10, then we'll move on to 8, then 5, then 2, then we'll move on to 9, and then 12. So from this array, our job is to reconstruct this tree. And so we'll pick this as a reference point and we'll start to simulate what happens for this tree. I think the first thing we want to get out of the way right away is that 10 is going to be the root of the tree. 10 is going to be the root because in pre-order traversal, we are always starting from the root node and only then going to the right and left children. So if 10 comes up as the first element, then it is most definitely the root. So let's go ahead and write this down, 10 as the root of the tree. Okay, now let's look at the second element, which is 8. From 10, we'll use the property of binary search tree and we'll ask, is 8 lesser than 10 or is it greater than 10? 8 is lesser than 10, so we'll put it over here. Similarly, we'll look at 5 and we'll ask the question, is 5 lesser than 8 or is it greater than 8? 5 is lesser than 8, so we'll put it over here. Now we'll look at 2. Is 2 lesser than 5 or greater than 5? 2 is lesser than 5, so we'll put it over here. Finally, we will look at 9 and we'll ask the question, is 9 lesser than 2 or is it greater than 2? 9 is greater than 2, so we'll put it over here. But this is incorrect. Why is this incorrect? Because there's something interesting happening. Look at this. Look at the original solution we had. 9 happens to be the right-hand side child of 8, not of 2. But from our logic, we were continually sort of moving down and down. And we realized that, okay, you know what? Still 9 is greater than 2. So 9 should come as a right-hand side child. But if you also note, 9 can be upgraded to 5's right-hand child. This still follows the condition that 9 is greater than 5. 5's right-hand child is greater than 9. Is greater than 5. So this is also a valid position. But we can also upgrade it to be the right-hand side child of 8. So this is also correct. Can we upgrade it further? We cannot. So 9 cannot be a right-hand side child of 10 because only values greater than 10 are allowed here and 9 is not greater than 10. So this is not for any use. Just remove it. So it looks like 9 is this position, and this position. Like we have 3 different positions for 9. Which of them is the correct one? We know that this is the correct one, right? So it looks like the highest possible value, the highest possible upgradable value is the answer we're looking for. Basically, you can also imagine it this way. If we had 9 over here, which would be incorrect, we have sort of set this boundary of, you know what, 9 can never be over this side. So it has to be the highest possible value over here. Okay. But now the bigger question is, okay, even if I consider the topmost value, which is going to be the answer. Why does this happen to be true? Why is the topmost upgradable value giving me the right answer? And if we can figure this out, we can get to the solution, because we will know for a fact that this works out. And look at this. This is correct. Okay. So let's try to simulate what will happen. Let's say that we will start off 9 from this point. We want to insert the value 9 inside of this tree. So the first decision we'll make is that, is 9 less than 10 or is it greater than 10? 9 is lesser than 10, so we'll move over here. Is 9 less than 8 or greater than 8? 9 is not lesser than 8, so we'll remove this. 9 is greater than 8, so we'll move it over here. And if you look at it, this is the right answer. So the topmost answer for upgradation is the exact same problem as inserting elements into the binary search tree, which means that we have indeed gotten a correct solution in our hands. But inserting is fine. Topmost is what we're actually doing. So let's try to focus on that. The first thing is, how do we even do this upgradation thing, right? We have to upgrade it twice. We have to somehow say that 2 is not a valid answer, 2 is a bad answer, 5 is a bad answer, and 8 is a good answer. How do we sort of go about moving this, upgrading this value of 9? One possible way is to use a stack. What this stack will do is basically we'll have the value 10. This way, we'll have the value 10. Then we'll add the value 8. So after 10, we'll get 8. Then we have the value 5. 5 is going to be appended like this. So we'll add 5. Then we have 2. So 2. And then when we have the value 9, which is greater than this value 2, we will pop this element from the stack. We can upgrade, we can say, okay, you know what? Even for 2, we can have it as the answer, but how about this? How about instead of 2, we get it to 5? We upgraded it, right? We're just looking at this in terms of stack. So we have popped out this value. Now I'll ask the question, you know what? 9 is still okay with 5 as the right side child, but can I upgrade it even further? Can I make 9 the right hand side child of 8 and pop 5? I can still do that. Now I'll ask the question, can I have 9 as the right hand side child of 10 and pop out 8? I cannot do that. So at this particular point of time, I'll say that, you know what, since I cannot go any further, 9 will be the right hand side child of 8. And in this way, we have sort of formalized what we're looking for. We first figure out that we wanted the topmost value. We want the topmost upgradable value. Then we figured out, okay, this is just the same as the, like using a stack, and we can pop out all the values that we don't need. At the end, whatever this last remaining value is going to be our answer. By the way, if you're still unclear, that's okay. I'll attach this link down below where you can go over and have a look. And this will sort of take you through the main key points again. I've also attached the code over here. Let's get started with writing the code. The first thing we'll do is set up the root variable, which we know is pre-order of 0. This will get us the values. We'll convert that to a tree node. And we'll return that at the end. This is what we're doing because we know for the fact that the first element in this pre-order array is going to get us the root of the tree. And we'll also have the stack initialized as the root value. Now we can start to go over all of the elements in pre-order one by one. So we'll say for value in pre-order of 1 all the way up till the end. So skip over the 0th index, start from the first index and then iterate over all of these values. We'll first extract out the child, which is going to be tree node of the current value. We'll also want to have the parent, which is going to be the stack of -1. So the top element in the stack is going to be the parent. And we also have this child where we want to insert somewhere inside of this tree. Now we'll compare the relations between parents and child to figure out where this child should go. And we'll say if parent dot value is greater than child dot value, Then we have a very simple case. Let's say that we only have 10 element in the stack. We only had this element and we wanted to add 8 to this tree. We'll compare 8 and we'll look at 10 and we'll say if child.value is lesser than 10, if child.value is lesser than parent's value, then it's very simple. We'll do parent.left equals to child. Once we set this up, we also want to move on to this current child value. So the stack gets appended with this child value. But the else condition is what makes this question hard. So let's actually go over it. This is the opposite case where the child value is greater than the parent value. In this case, as we saw before, we wanted to loop over and start to pop elements from the stack. So we'll compare the stack top value and we'll say if that is lesser than child.value. If it is still lesser than child.value, if we've already say popped a couple of elements and it still is lesser than child value, we cannot do anything. Let's just keep on popping. We'll also save that in the parent. At some point, we'll have the opposite condition. So let's take the case of 9 over here. So 9 comes up, it removes 2 from the stack, it removes 5 from the stack, and it will also remove 8 from the stack. It will only stop when 10 is the only element in the stack. In that case, we also need to do stack and, because stack -1 we're trying to access, so the stack should not be empty. Anyways, now that we have this, we can say that 9 is not actually a right hand side child of 10, but instead of the previous element that we popped, the parent is going to be the last element that is being popped. So we can do simply parent.right equals to child. And in this way, we have completed the entire logic. Let's try to run this and we'll submit this. Cool. So it gets us 63 milliseconds as runtime and 14.1 memory. Anyways, this is it for the solution. Construct binary search tree from Preorder Traversal. If you like this video, give it a thumbs up. If you have any more feedbacks, comments, suggestions, let me know down below. If you want to see more of it, subscribe. And as always, thanks for watching.